Interlocks are part of all power plant systems. They are devices which act to prevent or limit certain actions by other pieces of equipment and often act between two or more systems. Interlocks are safety devices designed to prevent costly operating errors or to restrict operational changes which could strain parts of the system. Knowing the various interlocks in any device is important. This driver may not realize that the starter switch of the car is interlocked with a small metal device called a key. Forgetting about interlocks can bring some red faces, especially if lack of action is thought to be due to a breakdown, when it really is only an interlock doing its own thing. Many common tools have electric interlocks, such as the spring-loaded switch on this drill and electric knife. These prevent operation except when the operator's hand is pressing the switch. Your TV set, for example, has a simple electrical interlock designed to prevent the user from getting too close to the high voltage sections when the power is on. These are known as permissive interlocks. They effectively prevent certain actions from taking place if those actions may endanger the system or the operator. One example of permissive interlocks would be found on this coal belt conveyor system. If the hopper feed starts before belt A begins to move, we might overload the belt and start spilling coal. The same problem would occur if the hopper feed and belt A start operation, but belt B remains stationary. Proper sequence would be to start belt B, then belt A, and lastly the hopper. An interlock between belt B and the motor control on belt A prevents belt A from starting out of sequence, and the hopper motor, of course, will be interlocked with belt A. Permissive interlocks, then, usually prevent something from acting normally or starting. A second class of interlocks trip or shut off equipment in the event a preset limit is reached or another part fails to do its job. A simple fuse is a type of tripping interlock. It breaks the circuit if the current draw exceeds the fuse rating. A circuit breaker does the same thing, though like most interlocks, it can be reset when the condition is corrected. A tripping interlock could act to stop coal feeding if either belt A or B happen to stop during operation, thus preventing this overload. The types of interlocks and their specific application vary widely in power plant equipment, and each equipment manufacturer builds certain protective interlocks into his equipment. Others may be specified by engineers who planned that part of the power interlocks. Obviously, then, we can only take a rather general look at interlocking devices in our power plant. The specific interlock plans will be something you must explore on your own. We'll look at some of the permissive and tripping type interlocks in the boiler system, in the turbine, and even look briefly at how some of the electrical system interlocks can affect us. First, let's look at the common permissive devices. These prevent steps in startup or shutdown from occurring out of sequence. There are several major steps in the boiler startup sequence. Does it matter if they don't proceed in order? Well, obviously it does, and an incorrect or incomplete sequence during startup may prove dangerous if, for instance, the fuel is admitted before the igniter is working. The plant boiler will be equipped with a number of permissive interlocks which prevent mistakes. For instance, before this forced draft fan will start, interlock devices may require that the induced draft fan is operating and that a negative duct pressure exists. The fan dampers or vanes must probably be closed to start up to reduce starting load, and if line voltage is low, the fan starter may be prevented from operating. Some interlocks contain a timing device to be certain that a minimum time delay occurs between certain steps in the startup. For instance, once the forced draft fan has started and is operating properly, a period of delay occurs, allowing any traces of fuels and flammable gases to be purged before igniters can be turned on. During this process, the boiler feed water or circulating pumps must also be put in operation, as ignition is interlocked with this system too. Before the igniter flame is lighted, interlocks will be certain that the flow of igniter fuel is satisfactory and pressures continue in range. Once the ignition is started, a detector may be interlocked to trip if a satisfactory flame is not seen. In a pulverized coal boiler, the exhauster will start next, but only if the interlocks report satisfactory igniter flames. Our pulverizer and feeders follow in their own interlocked sequence, and finally, the main flame starts. Like successive links, the chain of startup steps cannot function until each part is in order. Sometimes a small interlock can hold up a mighty big boiler system. Now, once the startup has been accomplished, various control systems of the boiler monitor and maintain how loads will function. For instance, what if the forced draft fan lost motor power? Well, before controllers could react, certain tripping interlocks would quickly cut off main fuel, ignition fuel, and damper back the induced draft fan, or trip it offline. Or if the induced draft fan fails during operation, tripping interlocks again cut off fuel to main burners and igniters, and unload or trip the forced draft fan. If furnace pressures or temperatures exceed safe limits, tripping interlocks will automatically initiate a shutdown of the combustion process. Trouble in the boiler water circulation system may cause interlocks to trip off all combustion. If the flame detector does not see a good igniter flame, it may trip out all combustion as a safety measure. The specific plans and details of the various controls and interlocks must be studied before the operator really begins to understand the operative characteristics of that particular system. Now about turbines. The turbine, or turbine system, is a device for transforming great quantities of energy from one form to another, like the boiler system. And also, like the boiler, the turbine will have been provided with a number of different interlocks, both the permissive and tripping types. Permissive interlocks vary widely in turbine manufacture, but like the boiler system, these prevent startup or shutdown of operational steps which are out of sequence. Or they allow time for pre-established time delays. These are often built in to guard against excessive temperature change rates. Once up to power, tripping interlocks stand ready to close down the steam throttle valves if something should threaten continued normal turbine operation. For instance, loss of boiler fans may initiate a turbine throttle trip to prevent any sudden change in steam temperature from endangering the turbine. And if water level in the boiler gets too high, a tripping interlock might close throttle valves before water could reach the turbine, or before there was a sudden temperature change. Interlocks with steam instruments can be set up to trip the turbine if sudden over-temperature or under-temperature conditions are detected. Vibration, especially in the low-pressure turbine, can become very destructive. Tripping interlocks are tied to excess vibration detectors. Pressurized oil systems for lubrication and operation of turbine controls are essential too. Interlocks not only trip if oil pressure drops, but may also prevent startup. Should stresses, such as excess movement of the spindle, either longitudinally or due to a warp or bend in the shaft. Even the governor is connected to an interlock, which prevents excess speed in the event of control failure. Normally, these are set for about 108% of normal operating speed. Each turbine or turbine system will have its own particular group of interlocks, and in our general look at these devices, we need to be aware of the generator's activities in making electric energy. The largest, most expensive interlocks in the entire electrical generating system are rapid-acting power circuit breakers, or switchgear. They interrupt the flow of electric power between the generator and the distribution system. Since the generator, by its nature, will try to supply power to any load on its circuits, heavy, sudden loads, such as fault currents, put strain on the generator and the associated turbine. The almost instantaneous action of the switchgear to remove the overload from the generator prevents damage. When the fault is cleared, the generator can again come online. During an electrical trip, the turbine throttles may also be closed down. This not only prevents overspeed, but saves steam energy until it can be used to generate power. When something trips off the turbine steam, the generator is unable to supply power to the rest of the system. To prevent the turbine generator from actually drawing power from the system, interlocks trip the circuit breakers open. Bringing a generator back into the main transmission system requires a wide variety of sequenced interlocks. These are examined in more detail later in this course. Wherever they may be located, or whatever they may be called, interlocks are designed to protect equipment and to save us from embarrassment or danger. So work with them, not against them. So let's put this program in neutral a while and turn to the quiz on page 30 of your booklet. When you've answered the 12 questions, start us up again. Okay, let's see if any of the questions tripped you. Score yourself correct if you answered true for number 1. Interlocks, no matter what kind, are safety devices. Some help prevent errors in control sequences during both startup and shutdown, so number 2 is true. 3 is false. A fuse is not a permanent. A timed interlock prevents a part of a sequence from coming too soon, so it must be a permissive interlock. Therefore, number 4 is false. 5 is true. Many types of tripping interlocks also act to prevent improper start sequencing, and so can be considered permissive devices at that point. In most start sequences where both are used, the induced draft fan is started ahead of the forced draft fan. Well, you should have answered number 6 as true. 7 should have been marked false. Unless the main fuel system is operating correctly and the igniter flame is satisfactory, the main fuel feed will not operate. A potentially dangerous situation like high water levels will probably not only trip the turbine, but also the feed water pumps and even the main combustion controls. Number 8 is true. Number 9 is false. Interlocks are not designed to bypass other safety devices. On the contrary, they should be bypassed only for special testing, never for operation. The answer for number 10 is true, but connected to several tripping interlocks, such as turbine throttle and generator breakers. The next one, number 11, is false. The generator and associated turbine will try to supply all the power called for by the transmission system. So overloads or faults on the electric lines put heavy mechanical stresses on the turbine and generator. This is why good switchgear interlocks are important to the whole power plant. Question 12, then, is true. Well, we went through interlocks in a general way fairly rapidly, so you may review this film on interlocks if you're not sure of the subject. Otherwise, begin to learn how the interlocks in your plant system operate.